So this is section 5.2, perpendicular and angle bisectors. So our objective is to be able to use the properties of the perpendicular bisectors and angle bisectors. So let's look at this first example here. So we have this diagram, and there's one key point that's just essential to understand. There's a special relationship between the points on the perpendicular bisector, which is this line right here, CD, and the segment endpoint, so our segment AB. So if we draw the line, so we've got line AC and we have line CB, I can look and I can take what I've learned in my previous chapters, and I know that these two triangles are congruent. So I know that triangle ADC is congruent to triangle BDC. Now, how do I know that? Well, I have side, angle, side, side, angle, side of the two triangles. So I know that these two triangles are congruent. What else do I know? Well, the key takeaway is that point C is going to be equidistant from both segment endpoints. Let me say that again. So my segment bisector, CD, my segment AB, point C is the same distance from A as it is from B. So I know that these two lines are congruent. So let's take a second and let's write down the definition of equidistance. So a point is equidistant from two objects if it's the same distance from the two objects. So it's really just the same distance from an object. Okay, so now let's go take a look at our theorem. So now we have the perpendicular bisector theorem. So all this theorem says is if a point is on the perpendicular bisector, so with this example, point P is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So that means that PA is equal to PB, or that those two segments are congruent. Now let's look at the converse of the perpendicular bisector theorem. So if a point is equidistant from the endpoints, so we can see that point P is equidistant from A, and it's also equidistant from B. How do I know this? They give me the congruent markings, so I know that PA is congruent to PB. Then it is on, so point P is on the perpendicular bisector. So I can come over here and I can, if I draw a perpendicular line, now what else does that tell me? Well, that also tells me that these segments, let's call this point M, that AM is congruent to MB. So you can always work backwards. This may be a little bit slippery, and it's okay to watch it again if you need some extra time. So let's go ahead and take a look at problem number 1. Okay, so all they do is they give me this diagram, and oh, I know that segment BD is a perpendicular bisector. How do I know that BD is a perpendicular bisector? Well, AD is congruent to DC, and angle BDC is a right angle. So what does that tell me about segment AB and CB? I know that they're congruent. So I can solve this by setting up 4x is equal to 6x minus 10. I'm going to subtract 6x from both sides. So I have negative 2x is equal to negative 10. Divide both sides by negative 2. So x is equal to 5. So I want to know the length of AB. Am I finished? Nope. I just know that my length is 5. So now I'm going to say 4 times 5. So the length of segment AB is equal to 20. What is the length of segment BC? It should also be 20. So if I plug that in, 6 times 5 minus 10, it's going to be 30 minus 10. So that gives me 20. Okay, on this example, a park director wants to build a t-shirt stand equidistant from the roller coaster right here and the spaceship chute right here. What are the possible locations for the stand? Okay, well, the first thing I'm going to do is I am going to connect these. So let's see if my pen will, and I'm going to do my best to do a nice straight line. Oops. Let me redo that. Okay, so I have my segment connecting the roller coaster and the spaceship chute. And I have found the center of the line. I've marked it right here, the little black dot. So my next thing is to draw a perpendicular bisector. So I'm going to get my straight edge. Oops. And I'm going to sketch that in. So we're just going to call this line, we'll call it line L. So any place on this point, which is what's cool about the perpendicular bisector of a segment, are all going to be equidistant from the roller coaster and the spaceship chute. So if I choose to put the point right here, it's going to be the same distance. So all of the possibilities are along the perpendicular bisector. So there are some places that wouldn't be good because, like right here where it runs into the merry-go-round, that wouldn't be a very good location for a t-shirt stand. But any place along here would be great. And it could even extend beyond. So we could draw it. And we could also look at it there. So I know that's not real straight. So any location that goes along the perpendicular bisector would put the t-shirt stand equidistant from the spaceship chute and the roller coaster. So this next thing we're going to talk about is the distance from a point to a line. So the distance from a point to a line is the length of the perpendicular segment from the point to the line. This distance is also the length of the shortest segment from the point to the line. So you can see here that the shortest distance from point B to this line is the perpendicular. If I were to go this way, that would be longer. So the shortest distance from a point to a line is the perpendicular to the line. So in this diagram, the second diagram, the distance, the shortest distance from point D to line AC is the perpendicular right here. So any other distance, no matter how close it is going to be longer. The shortest one is the one that forms a perpendicular. And so in this diagram, ray AD is a bisector of angle CAB. So if we measure the distance of the perpendicular segments from point D to the two sides, these are equal. So point D is equidistant from the two sides of the angle. Okay, so what we're going to do is we're going to take what we looked at in this example, and we're going to look at it in the angle bisector theorem. So if a point, in this case S, is on the bisector of an angle, then the point is equidistant from the sides of the angle. So in this case, S is equidistant from QS and from QR. So that means that segment SP is congruent to segment SR. Now let's take a look at the converse of the angle bisector theorem. So if a point in the interior of an angle is equidistant from the sides of the angle, then the point is on the angle bisector. So we have point S. We see that it's equidistant. We can tell by the markings. So SP is perpendicular to QP, and SR is perpendicular to QR. Then SP is equal to SR. So then we see that, okay, ray QS bisects angle PQR. So point S is on the angle bisector. And I know some of this may be a little slippery or hard to understand, but when you start using it, it'll start making more sense. So one of the things we see now, so now we want to find the length of segment RM. Well, it tells me that RM is 7x. Oh, I see I've got two perpendicular angles. And I can also see that ray in R is a angle bisector. How do I know it's an angle bisector? I see that this angle is congruent to this one. So what do I know about segment RM and segment RP? I know that they are congruent. So I can say 7x is equal to 2x plus 25. And I can solve and I can find out my value of x, and then I can find out the value of RM. So subtract 2x from both sides. So 7x minus 2x is 5x is equal to 25. Divide both sides by 5. So I get x is equal to 5. So I need to plug that into there. So 7 times 5 is equal to 35. So RM is equal to 35. Notice I didn't put the segment notation over it because we were talking about length. So this is our final answer.